Next up, we've got Joel, who will be speaking to us about inverting a binary tree with one line of Elm. So please join me in welcoming Joel. Thank you, Joel.
All right. So as mentioned, my name is Joël Quenneville, and we'll be looking at inverting a binary tree with a single line of Elm using the power of folding. So imagine you're going to an interview, and the interviewer asks you the following question. Invert a binary tree and do it on a whiteboard. So this is a notorious question that a lot of developers don't like, and doing it on a whiteboard is particularly painful because it's slow to write on a whiteboard. It's harder to fix mistakes. And so ideally you want something that's fairly short. So you pick up your marker, squiggle a few characters, and end up with this. A single line that inverts a binary tree. What is this magic? So the example I showed is 33 characters long, which admittedly I cheated a little bit by using single letter variable names to get it shorter. But even with a bit more expanded full word variable names, it's still 61 characters, which is comfortably a single line. So how does this work? Well, before we dig into how it works, let's take a quick overview of trees and how they work in Elm. So in Elm, we typically define a binary tree like this. So a tree is either empty, or it is a node that has a value and two children who are also trees. Let's look at some examples. So the simplest tree is an empty one. There's an empty tree, and that's all there is. Getting a little bit more complex, we might want to store a single value, the number 1. Now remember, all nodes must have exactly two children. So how do you represent just one node? Well, you make its two children empty trees. But they don't have to be empty. The children can be subtrees. So here we have 1 with a child 2 and a child 3. And we can just keep nesting arbitrarily deep to get any tree that we want. So now we have a basic grasp of how trees are usually represented in Elm. Let's look at the actual problem that we're being asked to solve. What does inverting a binary tree mean? What it's asking us to do is to flip the tree horizontally. You can think of it as this like mirroring. Notice in the two diagrams here, on one side, we have the red nodes on the left, and on the other, it's mirrored. The red nodes are now on the right. So let's walk through the process of how this is done. Typically, what you want to do is to visit each of the nodes and swap their children. In this particular starting tree, just for convenience, I've marked all of the left nodes in red and all of the right children in green. And notice how they move around when we start inverting. So if we stop art in the bottom right corner, if we look at that node 3 and we want to swap its two children, empty and 6. That has been done. Next, we would want to look at the two children of the node 2, so 4 and 5, swap them. And then finally, the root node 1, we would swap its two children 2 and 3. And that's it. We have inverted a binary tree. So back to that one-liner that we saw earlier. It looks like this, and all of the heavy lifting is done by the fold function. What is a fold and how does it work? Well, this is the signature for fold, and honestly, that's a little bit intimidating. There's some kind of nested function. There are a lot of type variables. So what exactly is going on here? We can break it up onto multiple lines to make it easier to talk about. And the first two arguments are really the confusing parts about fold. Some kind of function, some kind of value. We're not quite sure what's going on here. The third argument is the tree that's being folded. And then finally, we have our return value. So what I want to do is look at a series of 3 different mental models. You can think of them as different perspectives, different ways to look at what folding does and what those 2 mystery arguments mean, which will hopefully help you to get a better grasp of what folding is, what it does, and why inverting the binary tree using a fold works the way it does. The first one we'll look at is the idea of reducing. The second one is the idea of constructor replacement. And the third one is the idea of an abstraction over recursion. So starting with the idea of reducing. This is the way that folding is typically introduced to people and how a lot of people think about it. You take some kind of collection and you reduce it down to a single value, some kind of aggregate. This perspective is so common, in fact, that many languages even name their folding function reduce. So JavaScript, for example, does this. So some different ways that we might reduce a tree. We might want to get the sum of all of its nodes. So in this case, we've reduced a tree, which is a collection of numbers, down into a single aggregate number, 21, which is the sum of all values in the tree. But that's not the only aggregate we can take. We could also reduce the tree by counting the nodes and reducing it down to the number 6. We could also try to get the minimum or the smallest number in the tree and reduce it down to the number 1. So this idea gives us our first hint at maybe what those 2 arguments do. That first argument, the function, describes what kind of aggregation we want to do. Are we summing? Are we counting? Are we finding the minimum? And that second argument is our starting accumulator, which is sort of as we're going to gradually build up the aggregate value, what is the starting value for that? And here's an example of what an aggregating function might look like. So this function takes in 3 arguments, the current value of the node that we're looking at, a left accumulator. This is going to be the sum of the left subtree, the right accumulator, which is the sum of the right subtree, and adds them all together. So we add the value of our current node plus the sum of our left children plus the sum of our right children. And we would plug it in like this. This is how you would write the implementation for summing a binary tree. So we take our fold function, we plug in our add3 as the aggregation, and we're going to start our sum with 0. So that's the basic idea behind reducing as what fold does. All of these perspectives that I'm going to be sharing, we can go a lot deeper on them. And so I'm going to leave with some discussion questions, things that you can think about further, or even something to chat with me about later if you want to go deeper into that particular mental model. So in the case of reducing, a good question is asking what other common operators can be described as aggregations on a collection. A lot of things in software are some form of aggregation, and maybe more even than you think. So we've been looking at reducing as the idea of taking a collection, squashing it down into one value. But inverting a binary tree isn't really reducing it down. We're converting one tree into another tree. So you can kind of maybe squint and think like I'm reducing it into another tree, but that honestly breaks my mind a little bit. So let's look at a different perspective that can maybe give us a deeper understanding of what's going on here. This is the idea of folding as constructor replacement. This is probably the more technical of the 3 that I'm going to show, but it's also my favorite because I think it really unlocks some new insights into folding for me when I first learned about this. So going back to the definition of a tree, it's either a node or it is empty. And here, the node and empty are sometimes described as the constructors for a tree. They're functions that can build tree values for us. And their signatures look something like this. So the node signature takes a value and 2 child trees and uses those to build a new tree for us. Empty, you can think of it as a constant, you can think of it as a zero argument function. It just returns a tree. Now, let's take these signatures and make them a little bit more generic by changing all of the instances of tree with the generic type variable b. And you may think, this is weird, why is he doing this? But you may also think, wait a minute, this particular arrangement of letters looks vaguely familiar. And this is the signature for our fold function. Notice that first argument, the function, the second argument, they exactly match the genericized versions of our node and empty constructors. Coincidence? No. One way to think about what a fold function does is that you are giving it alternatives to the constructors for your tree. So that first argument is something that's going to replace node, and that second argument is something that's going to replace empty. Let's look at an example. So again, we have our add3 function we defined earlier that adds 3 numbers together. And if we try to sum a tree like we did earlier, through this new perspective, we might say that when we read this fold, we're trying to replace every node constructor in our tree with the add3 function, and every empty constructor with the number 0. We might have a tree that looks like this. And so if we just find and replace and go through, replace all of the node constructors with add3, and all of the empty constructors with the number 0, we end up with this expression right here, which we can then just start to evaluate. So starting from the innermost parentheses, 4 plus 0 plus 0 is 4. Then 2 plus 4 plus 0 is 6. 3 plus 0 plus 0 is 3. And 1 plus 6 plus 3 is 10. And there we have it. We have summed a binary tree from the perspective of constructor replacement, which is useful, but still doesn't tell us how we can convert a tree into a different tree using fold. So let's look at something slightly different. Here, in this particular fold, if we look at the first argument, it's saying replace node with node and replace the empty constructor with the empty constructor. Now, what do you think this will do? It will give us back the exact same tree that we started with, right? Every constructor got replaced by itself. This is not a useful function, but it does teach us an interesting lesson. We can use fold to disassemble and then rebuild the tree. And we could do that in the shape that we want. So we could define a function like this. It takes a value, a left tree, a right tree, and then just constructs a node with those arguments. This is identical to the capital N node constructor, but just as a sort of userland defined function. But it is identical to the capital N node. We might then take this and modify it slightly. Create inverse node. So inverse node takes the same arguments, but when it constructs the node, notice it swaps right and left. So right is now the first or the second argument to node, and left is the third. Now, if we pass this into a fold, we could read this from our constructor replacement perspective as saying, replace every node with inverse node, and replace every empty with empty. Let's walk through what that does. So we have this tree, and we're going to replace every node with inverse node. And then we're going to replace every empty with empty. Nothing has changed. And now we can slowly start to evaluate this. From the inside out, we're going to start by swapping empty and empty. That doesn't really change anything. And then we're going to swap node 4 with empty. And then finally, we're going to swap node 2 and node 3. And there it is. We have inverted a binary tree using fold. So we can take this idea a lot further. This perspective can help us understand different behaviors that fold can have, and also applying the idea of folding to other data structures. So a further discussion question would be, how can we apply this to other data structures? Now, if you have studied this problem before or have had to do it on an interview, the question in the back of your mind is, when is he going to talk about recursion? Isn't this a recursive problem? And our third perspective on what fold does is that it is an abstraction over the concept of recursion. If I were to write a recursion over a tree to do anything, to sum, to invert a binary tree, to whatever, most recursions are going to look almost identical. So in pseudocode, it would look something like this. If it's empty, we return some base case value. And it's important to return a base case because otherwise we could write an infinite recursion. Otherwise, we want to recurse on the left subtree, recurse on the right subtree, and do some action. Now, the only difference between summing a tree, counting the values, inverting it, mapping it, all of these different operations that are at their heart recursions, the only thing that's different are the base case and the action that happens at each step. We can write an abstraction over this and pull out only the two parts that change. And that's exactly what fold is. So from this perspective, that first argument, the function, is the action that happens recursively, the thing that happens at every step. And the second argument is our base case. So looking at inverting a binary tree again, but this time from the perspective of recursion, we might say that inverse node is the function that will get called recursively throughout the tree, and empty is the base case for our recursion. This particular perspective is really helpful because it tells us how to implement a fold. We can see here it takes in a function and a base case and a tree, and then cases on the tree. If we have a node, it's going to recurse left, recurse right, and apply our function. If it's empty, we return the base case. A particular mental model that's really helpful here is thinking in terms of layers of abstraction. In a lot of day-to-day work, if you have a tree library, you're going to be using higher level functions like map or maybe height to know how high the tree is. Maybe there's a tree sum that's built in, and those will be able to do your day-to-day work. If you need something that's a little bit more complex or a little bit more custom, you might drop to this mid-level and implement a new operation using a fold. And in fact, all of these high-level functions can be and usually are implemented in terms of fold. Fold itself, as we saw, is implemented in terms of recursion. So it is a sort of mid-level abstraction on top of recursion. And if you need something really, really custom, then sometimes you drop down to the bare metal and work on recursion itself. To take this idea further, a question we might ask is, what other abstractions could we build on top of the idea of recursion? Are there other things that might live in this yellow mid-level layer that might be useful? So to summarize what we've looked at, we've seen 3 different mental models and ways of understanding what fold does, and in particularly what those first 2 arguments for fold are. So these help us to understand what's happening, but also give us maybe a mental shortcut to help read code that's implemented as a fold. Those perspectives were firstly reducing, where the first argument is what kind of aggregation we're doing, and the second argument is our initial accumulator. The second perspective was constructor replacement, where the first argument is what was going to replace node, and the second argument is what will replace empty. And then finally, the idea of this being an abstraction over recursion. And so the first argument is the action we want to happen recursively, and the second argument is our base case. And to conclude, I will leave you with the implementation here of inverting a binary tree in one line of Elm. There it is. You'll notice I used the lambda form rather than calling our invert constructor. but it is identical just to make it work in line. So thank you so much for talking about trees and folding.
Awesome. Please join me in thanking Joel. Thank you, Joel. Okay. So once people have recovered the pieces of their blown mind off the floor, shall open it up for questions. So any questions for Joel?
I have a question, or more, I guess, a comment, where I just want to say that, like, at the beginning of this presentation, I thought, oh, I know this stuff. But you presented in a way that's much more clear, like where I understood it because I've worked with it so much, like, oh, it works this way because that's how it works. And then the other thing was, somehow I've managed to go, like, all my programming life with thinking that inverting a tree meant taking a leaf node and making it the root node. But it's more like, I guess, inverting is more like mirroring. So I learned that, and that's good.
It's inverting horizontally rather than vertically.
Yeah. Anyway, yeah, thank you. That was a really interesting talk.
Martin will now stop failing whiteboard interviews. Thanks for that, Joel. Any more questions for Joel?
Yeah, so I was wondering maybe how the unfolding is related to the fold. I use a lot of unfolding in my kind of generative stuff. And often it's infinite also, so I'm dealing with infinite structures, and then some folds work, but some don't. So, yeah.
Yeah, so I think what you're alluding to here is the idea that folds are an abstraction over recursion, but there are other abstractions that can happen, including unfolds, which are a separate family of similar things.
Yeah, I find this indeed this how you subdivide the different layers very useful, because I was indeed a bit confused, because at some point I also thought that like everything seems to be a fold, but actually indeed the most simple form seems to be recursion. And so the other ones are built on that, so that's very useful, because it can be confusing. And somehow also I always mix up the argument order, but I think when you look at it from a constructor point of view, then it becomes much easier to remember. So thank you for that. That's really nice. Yeah.
Yes, the constructor perspective is really helpful, like you said, to understand the order of the arguments. And then particularly when you're defining fold for your own custom types, to know what shape fold should have. You may have noticed that the one that I showed for a binary tree has one more argument than the one that you might be familiar with for a list. And that's because a binary tree has two children, whereas lists have one next value. And so the signature for fold is going to be slightly different from one data structure to a next. And following the constructor approach, the constructor replacement mental model helps you to figure out what shape the fold for your structure needs to be.
I had this feeling in the middle of the talk where I was like, wow, what a coincidence that the arguments and the constructors fit each other so well. And I'm trying mentally, but I'm unable to sort of extrapolate this to other structures that have 3 or 4 variants. And I'm trying to think will that mean that implementing the conceptual fold for that data structure is going to require an argument or function for every variant plus the base case, or not? And I'm curious if you've sort of taken this concept there and have done some of that thinking already, and that you can share.
I don't have a definitive answer. My sort of initial thoughts are yes, although I have seen some articles talking about this who don't, and who do things in a slightly different way. What's sometimes confusing when you're researching this topic is that people use terms slightly differently. And in some communities, folding means a slightly different idea. The idea that I was showing, the fancy term here is catamorphism. And so this idea of constructor replacement is that. And so my thinking is, yes, you would want multiple. So if you have 3 variants for your type, you would have 3 arguments to your fold. The more common version that I'll see is you still have 2 variants, but the number of arguments in the function are different. Or even I've done binary trees that have that empty might carry some data. And so the second argument in the fold then is not just a single value, it is a function that can process that.
Hey, one question from my side, just quite stupid question. So if you want to implement such fold function for such tree structure, we should implement it by ourselves, right? There is no in Elm standard package or any package that implements it for us. I mean, just stupid question because I saw that you're mentioning fold and it is like obvious stuff, but I just checked quickly packages. There is no tree structure, right? Standard structure, right?
So there are multiple third-party tree implementations out there. Trees are kind of a very varied family. So what I was showing is a binary tree, a tree that has exactly 2 children. But you could also have a quad tree where it has exactly 4. You can also have a multi-way or rose tree which has a variable number of children. And I believe there are several packages for all of these types and more that you might find on the Elm package site. If you have a very specific type of tree that you need, there may not be a package and you might need to implement it yourself. But for some of the more common trees, there exist third-party packages on the package website.
And basically it comes to recursion, right? So if you want to implement our own fold function, we need to go to recursion. Yeah.
Yes. Ideally, with most of these, you would only need to do recursion once to implement your fold, and then everything else can be implemented in terms of the fold. One of the benefits of that is that there are various tricks you can do to write your recursion in a safer way to prevent stack overflows. There's various tricks you can do to optimize performance. The one that I showed is a very naive implementation. And so ideally, you don't have to remember those tricks for every implementation of every function. You really optimize your fold to have a perfect recursion in there. And then everywhere else just uses the fold and doesn't have to worry about blowing the stack because they're not doing tail optimization or anything like that.
Good, thanks.
Okay, that seems like a good place to end it. So please join me once again in thanking Joel for his talk. Thank you, Joel.